Hey folks, today we're going to be doing more solving trig equations. We'll see a little bit of review from last time where we were solving equations by hand, drawing pictures, factoring, things like that. And we're also going to see some different types of equations that we'll actually solve graphically. Okay, so looking at this first one, very similar to what we did last time, we're going to solve from 0 to 2 pi and then generalize the solutions with those ones that we find. Okay, if there's a single sine, cosine, tangent, we want to get that by itself. Try drawing some triangles. If it's a special triangle we know, we should be able to find the angle easily, but if not, we'll use our calculator to help us. So starting out, because this is single cosine, we'll draw a picture. It's already by itself, where cosine can be negative. Remember, cosine are the x values, so that means to the left. So a triangle at the top left and at the bottom left. Alright, because this is 0.8, as a decimal you can write it as -8 over 10, or if you prefer just throwing it over 1. Okay, so -8 here, 10 on the hypotenuse. To kind of check yourself, making sure you have those in the correct quadrant, because even though this isn't a nice triangle we know, when we're using our calculator to find the angle, it's only able to give us one of the possible answers. Okay, but because this isn't a triangle we know, it would be okay to use our calculator in radian mode to get our final answer. Now I'm actually going to show you what the degree is here first, just to convince you that that's true. Using the inverse cosine for this one, we have -8/10. Just put 0.8 there. And it gives us this ugly angle. Okay, so you can write that down and convert by hand, but since we're just typing this in, it's just as easy to change that to radian mode, hit enter for our first answer. Now, a big reason why I wanted to show you this is because your calculator is giving us one of these 2 points. We always want to talk about measuring angles in radians, but what's important here is that it's positive. So that means we have to go counterclockwise to get to those points. So this 143 is actually our quadrant 2 value. Hopefully you remember from 5-2, our inverses, that the inverse cosine is only going to show up calculator values 1 or 2, so quadrant 3 wasn't possible anyway. Now that we know that, I'm going to go ahead and jot down this first number in radians to the nearest hundredth, so theta could be 2.50. And we're going to have to work a little bit harder to find this one. Okay, there's a couple ways we can do this. One way that kind of always works here, and I'm going to go ahead and write this down, put a pi over here for me, and on the right hand side put 2 pi. What you can do is always find this triangle angle using the number you have and either pi or 2 pi, whatever is closest to the point, kind of like what we do with exact values with radians. So here is regular pi, and what we want to do is find this angle, and to do that we just subtract off what we know already. So if you take pi minus that value, you can get the small angle that goes inside the triangle, and that's about 0.64. From there, we would be able to know that the bottom one's 0.64 as well, and then to get to this point from pi, you would add that. So then you can take pi plus that number to get our second angle, 3.79. Now I know these look weird, but remember pi as a number is about 3.14. 2 pi as a number is about 6.28, so you can use those to think about whether these numbers here are realistic for where they're placed on our picture. One other option here, and this is true for cosine only, we have some symmetry with our picture here. So this long arc from our calculator was 2.5, which means this long arc would also be 2.5. So a little bit of a quicker way to find the second angle for cosine. Once you take the inverse and get the first answer, I'm going to just bring that back up, All you have to do to find the second one is take 2 pi and go backwards that amount. So you can say 2 pi minus that angle instead of doing those 2 steps, and you come up with that same answer. Last thing we want to do, and we did this last time, is find the general solution. We can just stack these on top of each other. We'll say approximately. 2.50 was the first one, 3.79 was the second one, and we're adding 2 pi to each of these. That takes care of all of the other solutions that exist because there are infinite answers that work for us. And that's it for number 1. The next one is pretty similar. Again, we want to change this so we can put it on a triangle if possible. So 1.5 is 3 over 2. And we want to think about where tangent, the ratio, opposite over adjacent, can be positive. So we know everything's positive in quadrant 1. That's a gimme. Going to the left here, left and up would be negative and positive, so the ratio would be negative. Here we're going left and down. That would give us a positive ratio, and those are our 2 triangles for this one. So opposite is 3, this adjacent is 2. Here they're both negative, so negative 2 and negative 3 for this one. So signs flip-flop, but that's okay because it's the ratio that matters. Because this is a regular 3, it's not a special triangle we know, we want to just use the inverse. So inverse tangent of that 3/2. Again, because it's not a nice triangle, we know it's okay to just start in radians. If you're ever worried that it might come out nice, you can always change your mode to degrees and check it. That also helps you kind of give reference to what quadrant it's in if you're not quite comfortable with pi as 3.14. So here, because our calculator gave us one of the answers, you'll look at it, it's the 0.98, and that would have to be in the first quadrant since we had a positive value of 3/2. 0.98 here. And then we need to find the other one, again, just by using the picture. So tangent's kind of a special one where you can use the pattern in the picture to find the second solution no matter where your first one starts. Okay, so with this, tangent always has solutions pi away from each other or on the diagonal because technically the period for tangent is pi. So while we've been generalizing everything else plus 2 pi n, tangent really we can use pi instead. So first solution is just 0.98 from our calculator, and we'll just take that number and add pi to get the second one. So plus pi. Makes sense, it's a little past that pi 3.14, so 4.12 is our second solution. Like I was saying, because of this symmetry, we just need 1 to generalize. We'll just say plus 0.98, or 0.98 plus pi n, where n is an integer, instead of 2 pi. Tangent only for that. Alright, number 5 is a similar process to the last 2, so I want you to pause the video and try this one on your own. Alright, first thing we want to do here is divide by 5 so that the regular sign is by itself. Then again, it's the same process as we have been doing. We're thinking about where sign could be positive, and that's here and here, and opposite over hypotenuse. I'm hopeful that you didn't even need to get to this point to realize that this is a problem. We are not allowed to have the opposite side of a triangle be larger than the hypotenuse, so this one has no solution. None in the first period and none after that. Okay, so just no solution for that one. Anytime your ratio is greater than 1 or less than -1, for sine and cosine, we'll have no solution. Okay, that does not work for tangent, so be careful. Okay, number 7 is our first one of today that is new. And it looks a lot like what we did last time, but a really big difference is what's happening inside the argument of cosine. There is a number in front, And from Chapter 4, hopefully you remember that's called the a value, but it is the reciprocal of what number you see here. So our a value for this one is 1/3. And anytime we have an a value, that will affect our period. So we've been using 2 pi a lot for sine and cosine. When we have an a value, that's going to change it. Remember, our period formula was 2 pi times that a value, or 2 pi times 1/3, which gives us 2 pi over 3. What I want you to do, anytime there is an a value, so this is important, anytime there's an a value that's not 1, we're actually going to graph it. And what we need to do to graph it is actually change this 2 pi over 3 to degrees. The reason for this is, when we graph it, let's talk about the original cosine curve, not this one, but the original. Okay, when we graph it, we're going to talk about our solutions being these x-intercepts. But if you recall for the original, the x-intercepts at pi over 2, then at 3 pi over 2, and so on. Our calculator can't hold these numbers pi over 2. Instead, it has the decimal version of this, and we want to recognize exact values and only round when they're not nice values. So for that reason, we're going to use degrees, because if we see 90 degrees, we know how to convert that into pi over 2, whereas we wouldn't be able to change the decimal. So anytime we're graphing, we're going to use degrees. We'll just have to convert. In general, when you see pi, you can substitute 180, but I like to do it this way instead. This says 2 times pi over 3 is one of our common ones. So 2 times 60 degrees is 120. This is important for us because it's going to give our window for our calculator. Okay, so follow along carefully here, because we're going to use these same 3 steps on every one that we graph. Okay, so the first thing I want you to do is go to your y equals, and what we want to do is actually get this equal to 0. So we have to subtract over this 1, and we'll type in 2 cosine. Now, I'm going to do this now, but I'll explain it when we actually go to our calculator. But it's 2 cosine 3x, close it, square it, minus cosine 3x, and then we subtract it over that 1. The reason I'm going to have you subtract it equal to 0 is so that we can look at the x-intercepts for our answers, and so that we don't have to adjust our y values on our window as often. Okay? So when we type this in 2 cosine, the first thing your calculator does is open a parenthesis. That's why we're moving that squared after the fact, because it won't let us write it before. So then 3x, close it, square it, minus cosine 3x, close that one, and then minus 1. From there, in your y2, I want you to put 0, and that's going to stay for all of these. It lets us find the x-intercepts a little bit faster by tracing the intersections. Okay, once we've typed it in, that's step 1. Step 2 is going to be adjust the window. Okay, so go to your window. I'm going to tell you the things that are always going to stay the same first. So what I want you to do, because we're going to go 0 to 2 pi most commonly, or 0 to the period, what I want you to do is go 0 for this one, and the x maximum is actually going to be our period. I'll come back to that. For your y min and y max, I want you to change them from -5 to +5, and we're not going to adjust those any of these times either. Okay, that should be plenty of room for us to see the whole curve, even if we do have an amplitude change like this 2 stretches out our total height. Okay, so going back to the x max, we're going to set this to our period. Our period was 120, so that's what we're going to use. Again, you want the degree version, not the radian version. And with that in mind, our very last step is to make sure our mode matches our window, and it has to be degrees. Then go ahead and hit graph, and you'll see the curve. Now, one thing I didn't adjust here, and you can tell by my x-axis, This thick bar on the x-axis is because in my window I'm counting by ones. If you want to change that to 30, that might make it look a little bit better and let us see kind of our scale as we get to that 120. I chose 30 because it's one of our nice triangle values and it's good to get to our 120. So looking here, our solutions are going to be all of the times the curve hits the x-axis. It looks like there are 4 total, 1 at the beginning, here, here, and 1 at the end. Okay, what we want to do is just trace the intersections. Second trace, and then number 5, you can type in 5. Okay, I recommend starting way at the left and then just working your way through the numbers. Okay, so I'm going to scooch over here, get close to that first one, and once I'm close, just hit enter 3 times. Went a little bit far, it looks like. But enter, enter, enter. Alright, looking at this, I want to point out something that will happen sometimes. It sometimes happens for X, but most commonly, if you're going to see it, it's going to be on Y. Anytime you see E, that is error for 0. So this just says 0, 0. To check that if you're ever worried, you can hit trace and type in 0, and that'll show you it's 0, 0 if you're ever concerned. But our first one is 0 degrees. We're just going to write them down as we go, and then we'll convert them to radians as instructed. Alright, second one is second trace intersection again. Notice right now you're on the curve. If you go up, you'll be on the line y equals 0. It lets you travel a little bit faster if you want to get closer to that second intersection. Then enter, enter, enter again. The next one is 40 degrees. And then we're just going to continue this process. Second trace intersection. Moving over on the line. 80 degrees. And there's one more there, way at the end. Now, I moved my window just a little bit by my arrowing over, so yours should be right at the edge. Mine's a little bit before. Try that one more time. There we go. Should work now. And then just enter, enter, enter. And this one, another example of things you might see on your calculator. If you see a bunch of 9s or if you see a bunch of 0s, it's really error. Again, you can check yourself by hitting trace and doing your 120 to get that x-intercept nicely. So those are our 4 solutions that happen in the period. What I'm going to have you do is, it asks for 0 to 2 pi, but really that's just in general in the first period is all I want there, and then we're using that to generalize. I have 0 to 2 pi because that's the most common period for these things. When you have an a value, that will change. You don't have to change to get the extra ones. Last step, what we're going to do is when we're graphing in degrees, we still have to final answer in radians, and these are not our common radian values that we can convert easily. Like 30 degrees, 45, and 60, we know they're radian values. So in general, we're going to convert by hand the same way always. So first, 0 is just 0. We don't have to worry about that. But what you'll do to convert to radians is divide by 180 and change it to a fraction, and we'll throw that fraction with pi. So the first one up is 40 over 180. 4 over 18 is 2 over 9. Tack on the pi. We don't want to type in pi unless this fraction's really ugly. We'll see that happen today. The next one will be 80 over pi, so that's 4/9 pi. And then the last one is 120 over 180, 12 over 18, 6 goes into both of them. It's 2/3 pi. That is one of our more familiar ones. Okay, but if you notice, each time we were adding 40 degrees here, we decided 40 degrees was 2/9 pi. We can actually generalize this by saying 2/9 pi n, where n is an integer. Because that's how often they happened, and our first one is at 0. It'd be equivalent to say 0 plus 2/9 pi, where n is an integer, because of this common pattern, but 0 plus anything is just the anything. Okay? There would be no problem if you wanted to write all 4 of these out and then just add the 2/3 pi from our period. Okay, that's one thing you do have to watch for. When you're generalizing these, you can't just assume it's 2 pi. You have to use the period that we found in the first step. Okay, so be careful for that. Alright, next up, another example where we see an a value. Remember, the a value is the reciprocal, so for this it's 1/4, and that changes our period. Okay, so our period will be found, just like last time, taking 2 pi times that reciprocal, and that is pi over 2. When you have an a value, we are graphing. There is a way to solve these algebraically, but it's a little bit more work than worthwhile, so we're going to do these by graphing as well. So again, we'll graph, and we want to make sure that this is in degrees instead, so hopefully you recognize pi over 2 as 90 degrees, and we can go type some stuff in. So going to the y equals, clear out that equation, and we're going to set this equal to 0 to solve. So cosine 4x, close it. Anytime you see theta, it's good to replace it with x. And then we have to subtract this over, so minus 0.6. Okay, then we're going to change our window. Mine looks funny because I arrowed over too far, that's my bad. Yours should be 0 and 120 from last time, but for this one we want to change it to 90. So 0 and then 90. The rest you should not have to change for these problems. Okay, our mode from last time is in degrees. We want to double check that. Let me just show you what happens if you're in the wrong mode. You'll be able to catch yourself because of how the graph looks. It's crazy, it cycles super fast, so it will be obvious when you are in the wrong mode when you're graphing. Okay, so I'm going to go ahead and switch it back, and then same process as the last one, we're going to trace intersections. There is something different about this one, and we'll see it as soon as this pops up here. We only have 2 solutions because it was a regular cosine, not a squared, but when we go trace these intersections, at the left here, you'll notice that that's not a nice degree value like the last one. Okay, we still want to write them down, but what I want you to do when you write them down is actually put all of the decimal places, because what we're going to do is, for these ones, when they start ugly, they'll end ugly. These ones will round to the nearest hundredth, whereas the last one was nice and exact. Okay, so all of the decimal places, just jot them down. Okay, do that for the next one as well. Because this cosine was equal to a 0.6, if that 4 wasn't there, and we're thinking triangles, that's not a triangle we know, not 1/2, radical 2 over 2, or square root of 3 over 2, and that's what told me it wasn't going to be a nice angle. Okay, again, just jot this down, all of those decimal places, and we'll just convert like we did last time. We only have 2, so it's not so bad. What's different on this one, when we divide by 180, instead of just adding the pi in our answer, we're actually going to multiply by pi in our calculator. Alright, so go ahead and get out of there at that point, and I will tell you, if you hit second and then answer, it will bring up that last angle, so you don't have to retype it. I just didn't want you to have to get out of the graph twice to do that. It's a little bit more work, so that is a feature you can use. So I'm going to do that one first. divided by 180, and then I want to actually times pi for this. The reason is I don't want to put an ugly decimal with a nice pi together in my answer. We're just going to have one ugly decimal for the final answer. So this one is 1.34 to the 100th, and we're doing that same thing with the other one. I can't use the answer on this one unless I go back to my graph. I'm not going to do that. I'm just going to type it out. Divided by 180 and times by pi. Oops. Okay, and my first one was 0.23. We'll say approximately, and then we'll generalize by stacking them on top of each other. So theta is approximately 0.23 plus the period. Now, be careful when you're generalizing. We have to use the period in radians, not the degree one. So it's pi over 2n, where n is an integer. And then the second one, same way. 1.34 plus pi over 2n, where n is an integer. Okay, and really those are the toughest ones in terms of graphing, when you have those ugly decimals that you have to take that extra step to convert with. Alright, looking at the next one. Okay, sine we want to get by itself. Dividing by 2 here. Sine is a negative 1/2. That's a draw picture one. Remember, we're only going to graph when we see an a value that makes things a little bit weird. And there's actually one more instance, which we'll see here in a little bit. So this one is sine is negative 1/2. I want you to pause the video and take care of this one for me. Sine is negative in quadrant 3 and quadrant 4, because the negative means going down here. This is a 1, 2 square root of 3 triangle. All we really need is the angle across from the 1 is 30 degrees. So we want to think about this in radians. 30 degrees is pi over 6 in radians, so I'm going to call this 6/6 instead of 1 pi. So that would make this 1/6 more than that, or 7/6 pi. Similarly over here, instead of calling this 2 pi, I want to say something over 6, and 12 over 6 is 2. But I need to back it up because it's not quite there, so this would be 11/6 pi. Those are my two answers. There's not a common distance between the two, so to generalize, you just stack them on top of each other. Use a hard equal sign for these ones since they are not approximate, and we'll just tack on 2 pi n. Okay, so review from what we did last time. Alright, so number 13 is one that almost looks like what we did last time, but instead of this being squared, it is a 2 theta, so it is an a value. But what's different about this one versus the first a value problem we had is the a value doesn't stay the whole way through. So this is a special case. So this first one says the a value is 1/2, whereas the second part says a is 1. This would say that the period is 2 pi times 1/2, which is pi, and this one just has a regular 2 pi for the period. So really, without graphing, there's no way to determine which one of these is actually the period. With that in mind, we want to use the bigger one. So if you're ever in doubt about what window to choose with something like this, use 2 pi or 360 degrees to graph it. Alright, this one's already equals 0, so in your y equals, let's go ahead and get that typed in. Alright, window, we're changing just the X-max to 360. And then we are going to double check the mode in degrees. Then graph. We want to find all the times this thing crosses the x-axis. I do want to take a second to talk about the period. So here, if you split this thing in half, you would, let me go ahead and draw on it here for a second. If we think about 180, it's directly in the middle of this thing, but at 0, we start at the max and go down. This one does not start way up here. It doesn't repeat itself afterwards like we started. So that means that we really did need this whole 2 pi because we don't see the same curve repeat at that halfway point. So with that in mind, we got to find all of them, and it looks like there's 4 total because there's 2 right next to each other here. We're just tracing intersections. Second, trace intersect. I'm going to start way at the left and work through these. First one is a nice 90. Just jot them down and then go and convert them. Second one is 120. Third one is 240. And I'm guessing this next one is 270. It is. Okay, what I want you to do is pause the video and see if you can finish this one. There's not a common distance between all of these, so after you convert them, just stacking them all on top of each other is really the best way to go here. In radians, we've got pi over 2, then we've got 2 pi over 3, 4 pi over 3, and 3 pi over 2. Remember, if you're not sure what it is, divide by 180, tack on a pi. Okay, it gets you the 1/2, the 2/3, the 4/3, the 3/2. Just make sure you write it as a fraction rather than a decimal. From there, you just separate all of them, stacked all on top of each other, one by one. Now, in this case, there is a way to actually group these two, but when you're graphing and you can't see a clear pattern between all of your solutions, I want you to just write them out separately. That way, there isn't something going on that maybe we don't see kind of messing with us. So just plus 2 pi in on all of these, where n has to be an integer. And that's about as messy as it can look in terms of solutions. Alright, just a couple more here. We've got a cosine 3x equals 0.724. Again, this has an a value. We've done a couple examples like this where there's an a value. I want you to go find the intersections and write them down. I will help you when you get to that point. Alright, so our 2 intersections, ugly decimals, I knew that because this was an ugly decimal, not a triangle we recognize, but there are 2 solutions just like when we have regular sine, regular cosine, regular tangent normally. Okay, remember, what you want to do for these is write the whole number down, and then you just divide by 180 times by pi. Okay, because there aren't parentheses around that, that really does say times by pi, so it gives you that right order of operations. Okay, so those are your 2 solutions in radians after doing that. Then, just generalize like we have been doing. Okay, stack them on top of each other. We have approximately because we rounded, but remember, our period was different here. Window was 120, but we want to use the 2 pi over 3 n for the general solutions because we want the radians. Okay, just a reminder, if you didn't get your window adjusted, the period comes from 2 pi times the reciprocal of that thing, 2 pi over 3. Alright, first one of what I kind of warned you about, there were 2 instances where we would graph. One of them was where there's an a value. The second one that we're going to graph is if you see both sine and cosine or any 2 different trig functions, we're going to graph those as well. And for these ones, we're just going to graph with 360. That's going to work almost always for us. So going into our y equals, we want to get it equal to 0, just like we have been doing. Cosine x, this is a case where we put the squared after, because it won't let us type it in first. So squared, and then we're subtracting over the sign, so minus sine x, close it, square it, and we'll add over the 1 plus 1. Feel free to write that down on your paper if you can't do that as you go here. Then window, I'm going to change back to 360, and the mode we shouldn't have to change. Alright, looks like we have 2 solutions here. One thing I haven't mentioned yet, you can, if you are careful, use your scale to kind of count where they are. So with this one, I want you to notice a couple things. So first up, if we're counting by 30s, that looks like 30, 60, 90, and you can always just trace 90 to see if you're right, and there it is. So that's one option. Another thing I want to show you here is I told you that for these types we're just going to assume 360 and kind of see, but almost like that last one where we couldn't determine on number 13 whether it was supposed to be pi or whether it was supposed to be 2 pi. Sometimes when you have a squared term, that same thing happens. Sometimes it's 360, it's 2 pi, or sometimes it's only half of that. If you notice, at this halfway point of our window, you see the exact same curve on the right-hand side. So really, this period is only 180 instead of 360. But again, like I told you, we'll just do that 360, and we'll be a little bit repetitive, but we don't miss any problems, and we'll go ahead and write down both of them. So this one was 90. That second one over there, based on our period being 180, should be 180 past that at 270. Okay, but I'll just go ahead and trace that intersection right along the curve. It goes a little bit faster. Just get closer to the second one. Enter, enter, enter. And it really is, once it pops up, it really is at 270. A little bit of extra change there, but that's just your calculator's error. Okay, again, if you hit trace with that 270, it will show you it's exact. Then we change them to radians. Those are nice numbers we know. Pi over 2, 3 pi over 2. If you don't know that, you know the trick. And then we'll stack them on top of each other to finish the general solutions. Because we graphed with the 360, we're going to use the 2 pi n for the generalized solution. Same thing for that second one. And that's it for that one. Last one here, we've got cosine 2x equals a negative 1/2. Okay, very similar to what we have been doing. The a value is happening, so we're graphing it. Let's find our period so we know what to graph our window as. Multiply by 2 pi. 2's cancel, and we're left with pi, or 180 degrees. Okay, in our y equals, we're typing cosine 2x, and then you're adding over that 1/2. Now, because this 1/2 is one of our nice triangles we know, even though this 2x is there, we should have nice angles pop up for our solutions, and we'll see what they are once we adjust a couple things here. So we want our window adjusted to 180, go into X max, and then just making sure your mode's in degrees, because this whole test you'll alternate back and forth. So then graph, we should have 2 solutions just like regular cosine, and we just have to go find them. Sine, or second trace intersection. nice at 60 degrees. Second one, and at 120. Change them to radians, pi over 3 and 2 pi over 3. Those are common triangles, but if you don't know them instantly, just divide by 180. And finish up using the period. Our period on this one, remember, was pi, so plus pi n, where n is an integer. And the second one is 2 pi over 3 plus pi n, where n is an integer. Okay. What I want you to be careful on here, these are 60 apart, but you don't necessarily know all of them are 60 apart. I know that they're not, in fact, because there was not one at 0, then to 60. So remember, when you're graphing them, just use the period. Don't try to do anything fancy past that. The rest, the eat-ins, and then the review below are yours for homework. Please feel free to come see me if you have any questions.